Welcome back to the deep dive. I have to admit, looking at the stack of research notes and lecture slides and technical breakdowns in front of me today, I feel a little bit like I've wandered into the wrong classroom.
Oh yeah, it's a lot of material.
It is. And we aren't just skimming the surface today. We are looking at what I honestly consider to be the closest thing to actual magic in modern technology.
It definitely feels like magic, doesn't it? Well, until you actually peel back the curtain. Then you realize it's not magic at all. It's just a lot of really, really aggressive calculus.
Which is exactly why I brought you in, to translate all that calculus into plain English for us.
I'll do my best.
Today we are stripping away the mystique. We are basically going back to school. Specifically, we're stepping into a university-level seminar on computer vision.
We are. And I really want to set the stage properly here, because this isn't just a technical discussion about, how do cameras work?
Right.
This is about a much more fundamental, almost philosophical question. How do you teach a rock to see?
A rock.
Silicon. It's a rock. I mean, it's sand, basically.
Oh, right, okay.
We are trying to teach a slice of silicon, which is blind and deaf and only understands binary math, to look at a photograph and say with absolute confidence, that is a golden retriever.
When you put it that way, the stakes feel a lot higher. I think most of us, and I'm totally including myself here, take our own vision for granted. I look at my dog and I just see a dog.
Right, it's instant.
Yeah, instant and effortless. I don't feel my brain crunching numbers or, running algorithms in the background.
And that is the great illusion of human consciousness. You don't feel the processing, but your brain is actually doing an incredible amount of heavy lifting.
Really?
Oh, yeah.
Yeah.
Evolution has spent millions of years optimizing your visual cortex to recognize patterns, detect edges, understand depth. You are essentially a biological supercomputer for vision. You just don't have to read the code.
And the computer. I assume it's starting from scratch.
Worse than scratch, actually. It's starting from a place of total, absolute blindness.
What?
There is a massive disconnect, what we call the cognitive gap, between human vision and computer quote-unquote vision. To a computer, that image of your dog isn't a furry friend. It isn't even an image.
What is it then?
It is a giant, chaotic, terrifying spreadsheet of numbers.
Okay, so that's our mission today then. We need to figure out how we bridge that gap.
Exactly.
How we get from that spreadsheet of cold, hard numbers to actual understanding. Like to the point where the machine actually knows what it's looking at.
And to do that, we're going to break this down into 4 distinct modules, effectively following the syllabus of a graduate-level course. I'll play the role of the professor, and we'll treat this like a proper seminar.
I've got my notebook ready. Give me the roadmap. What is on the syllabus for today?
Okay, so Module 1 is the raw material. We have to understand the atomic units of this world, pixels and matrices. If you don't understand the data structure, you can't understand the AI. You have to know what the input looks like.
Okay, makes sense. Start with the basics, then Module 2.
Module 2 is the old school method, though old in AI terms means, about 10 years ago.
Right, ancient history.
Exactly. We call this the Lego theory. This is the era of convolutional neural networks, or CNNs. This is how we teach machines to build objects out of simple shapes.
Oh, I've heard of CNNs. They're kind of the workhorses of the industry, right?
They were the undisputed kings until very recently, actually. Which leads us perfectly into Module 3, the paradigm shift. We're going to talk about vision transformers, or VITs.
VITs, okay.
This is a completely different way of thinking. Instead of scanning an image like a grid, we treat it like a language. We treat a photo like a book.
Treating a photo like a book, that sounds entirely counterintuitive, but I'm intrigued. And the last one, Module 4.
Module 4 is the universal language. This is the payoff. This is where we talk about embeddings and multimodality. It's how we finally got text and images to speak the exact same mathematical language.
Which is what powers tools like ChatGPT's Vision or Google Lens today.
You got it.
Okay, that is a heavy lineup, but I'm ready. Let's not waste any more time. Let's start at the very bottom. Module 1, the raw material.
Let's do it. I want you to perform a little mental exercise with me. Imagine we are in a dark lecture hall. I pull up a slide on a projector. It's a picture of the letter A.
The letter A, got it.
A big, bold, black letter A on a pure white background.
Okay, I'm visualizing it. First letter of the alphabet. Maybe in like Times New Roman.
Sure, let's go with a nice serif font.
Yeah.
Now, when you look at that day, your brain immediately fires a neuron that says letter A. You associate it with a sound. You associate it with a word. You might even think of amble.
Yeah, it's automatic.
But if we peel back the user interface, if we look at what the graphics card is actually sending to your monitor, what is it really?
It's a grid, right? Like a mosaic tile floor.
Exactly. It's a raster. Think of it like a sheet of graph paper, a very, very fine mesh. And inside every single square of that graph paper, every single pixel, there is a single integer, a whole number.
Okay, so this is what you call the matrix reveal in the source notes.
Correct. We are revealing the matrix. We aren't looking at ink on paper. We are looking at light intensity values. In the most basic black and white system, typically we use an 8-bit scale.
An 8-bit scale.
Right, where 0 represents pure black total darkness.
Yeah.
And 255 represents pure white maximum brightness.
Wait, what's 255? That seems like such an arbitrary random number. Why not a clean 100 or 1,000?
It's not arbitrary at all, actually. It's binary. Computers think in bits. 255 is the maximum value you can store in 8 bits of data. It's 2 to the power of 8 minus 1.
Oh, okay, so it's a hardware thing.
Yeah, it's purely an efficiency thing for computer memory. But for our purposes, you just need to remember the scale. 0 is black, 255 is white.
So if I look at that letter A again, the computer doesn't see a shape at all.
Yep.
It just sees a cluster of zeros in the middle of a sea of 255.
Exactly. If you were to read this image out loud to the computer, you wouldn't say, hey, it's an A. You would start at the top left corner and read every single row. You'd say 255, 255, 255. Oh, here comes A000 back to 255.
I'd be reading a massive, totally boring spreadsheet of integers.
And this is the first critical realization of the course. An image, digitally speaking, is just a list of numbers. It has no inherent visual properties to the machine. It is data, and data is blind.
Okay, that makes sense for black and white. It's simple, light or dark, but the real world isn't grayscale.
True.
I'm looking at a photo of a human eye right now in our source material. The human eye slide. It's got texture, it's got color, it's got nuance. There are browns, greens, little flecks of gold. How does all of that fit into the spreadsheet model?
That's where it gets really interesting and where we have to expand our mental model a bit. We tend to think of photos as flat 2D objects, like a physical print you hold in your hand.
Because they look flat on a screen.
Right. But to a computer, a color image is actually a 3D object. It is a volume. We call it a tensor.
A tensor, okay. That sounds like something straight out of a physics nightmare.
It does sound intimidating, but in this context, just think of it as a multidimensional array, a cuboid. Imagine that graph paper again. For a color photo, you don't just have one sheet of graph paper. You have 3 sheets stacked perfectly on top of each other.
Oh, I'm guessing those correlate to red, green, and blue.
You got it. The RGB tensor. The bottom spreadsheet tracks the intensity of red in every pixel. The middle one tracks the green. The top one tracks the blue.
So let's trace a specific pixel to make this concrete. If I look at, say, coordinate 10 row 10, column 10, and in the photo, that pixel's a really bright orange.
The computer drills down through that stack at coordinate 10, 10. On the red layer, it finds a value of, say, 250, so very high intensity. On a green layer, maybe a 150 medium intensity. On the blue layer, maybe a 0.
And then the monitor combines those 3 numbers to blast that specific custom shade of orange right into my eye.
Precisely. So every single dot on your screen is actually a vector of 3 numbers, a little vertical stack. And this structure, this 3D matrix of height by width by channels, is the fundamental data structure of the visual world.
Height by width by channels. I see that written here as the technical spec.
That is the holy trinity of computer vision data, and it has strict rules. It has a fixed grid topology, meaning the pixel at row 10, column 10 is always physically next to row 10, column 11. Neighbors matter.
Right. Contrast that with a regular spreadsheet of, like, financial data. In a financial spreadsheet, row 10 might have absolutely nothing to do with row 11.
Exactly.
One could be Q1 earnings, and the other could be employee headcount. But in an image, row 10 and row 11 are spatially linked. They have to be.
They do. That spatial consistency is the only reason we can make sense of it. And here's the massive thing. But that ends module 1. Despite all this structure, despite the RGB layers of the grid topology, the algorithm is still completely blind.
It has the numbers, but it doesn't know what they mean.
It has 0 clue. It doesn't know that that stack of numbers represents an eye. It doesn't even know what an eye is. It doesn't know that eyes usually appear on faces. It just knows that at coordinate 10, the value is 250, 150, 0. It calculates, it doesn't perceive.
It feels like we've really just defined the problem here, not the solution. We've turned the world into a massive pile of data. Let's put this in perspective for the listener. A modern 4K image is what in terms of size?
A standard 4K image is roughly 300 and 840 by 200 and 160 pixels. That's about 8.3 million pixels total. Now multiply that by the 3 color channels, you're looking at nearly 25 million numbers.
25 million numbers. For one single frame.
For one single frame. And you want the computer to look at those 25 million numbers, find the hidden pattern instantly, and say, cat.
That sounds literally impossible. It sounds like looking for a needle in a haystack, but the haystack is entirely made of math.
It sounded impossible for 50 years. Which brings us to Module 2, the solution. We call it the Lego theory of perception.
Okay, I'm a big fan of Lego, so I'm hoping this is as fun as it sounds. But why Legos?
Because it's a perfect metaphor for how we bridge the cognitive gap. We need to move from pixels to patterns. Think about your own brain again. If I show you a picture of a car, your brain doesn't process 25 million individual dots.
No. I see a wheel. I see a windshield. I see a bumper.
You see shapes. You see geometry. Your brain is a feature detector. You instinctively break the object down into its constituent parts. We needed to teach the computer to do the exact same thing. We needed to teach it to stop looking at the individual numbers and start looking for the shapes they form.
So we were essentially teaching it to find the Legos hidden inside the matrix.
Correct. If the computer can find enough circular Legos, which might be wheels, and some rectangular Legos for windows and maybe a metallic texture Lego, it can statistically infer, hey, this is probably a car.
And the tool we built to actually do this is the CNN.
The convolutional neural network. For about a decade, from roughly 2012 to 2020, this was the absolute gold standard in AI.
Yeah.
It actually mimics the human visual cortex.
How does it work, though? I mean, mechanically, how do you find a circle in a spreadsheet of 25 million numbers?
You use a mechanism called the sliding window, or technically the convolution.
Paint the picture for me. How does the window slide?
Imagine you have that giant spreadsheet of 25 million numbers representing the image. But let's say the room is pitch black. You can't see it all at once. You only have a tiny little flashlight that can shine on a small 3x3 square of pixels at a time.
Okay, so I'm just looking at a tiny patch, 9 pixels total.
Right. You start at the top left corner, you shine your light, you look at those 9 numbers, then you slide the flashlight one step to the right, you look at the next 9 numbers, you slide again, you scan the entire image row by row.
Scanning the grid. Takes a while, but okay.
But here's the trick. This isn't just a normal flashlight, it's a filter. Think of it like a sieve or a stencil. This 3x3 grid has its own numbers baked inside it. It's a mathematical trap designed to catch one specific thing.
Give me an example. What is it trying to catch?
Let's say this particular filter is a vertical edge hunter. The numbers inside the filter are arranged specifically. Maybe a column of negative numbers on the left, zeros down the middle, and positive numbers on the right.
Okay, so it's a pattern of numbers explicitly designed to react to a vertical line.
Exactly. As you slide this filter across the image, you perform what's called a dot product. You basically multiply the filter's numbers against the image's pixel numbers and sum them all up.
I am having a serious math class flashback right now, but keep going.
Think of it as a resonance test. If the filter lands on a patch of plain white sky, all the pixels in that area are the exact same color. The math just cancels out. The result is 0. The filter says, nothing to see here. It stays totally silent.
Silent. Got it. Because there's no edge.
But if the filter lands right on the edge of a building, where you have bright white pixels right next to dark shadow pixels,
The numbers are different.
the numbers clash violently. The math suddenly spits out a huge positive number. The filter effectively yells, I found one. I found a vertical edge right here at coordinate 50-50.
So as you slide the single filter across the whole image, you're basically creating a map of where all the vertical edges are.
We call that a feature map. But remember, that's just one filter. A real CNN has dozens of them just in the very first layer. One hunting for vertical edges, one for horizontal edges, one for 45-degree angles, one for color gradients.
It's essentially breaking the image down into a rough sketch.
Exactly. Layer 1 reality is just lines and curves. It's a sketch. But a sketch isn't a car.
Right. A vertical line could be a building, a tree, a person, a lamppost, anything.
So we have to go deeper. We take those feature maps from layer 1 and we feed them into layer 2. Layer 2 doesn't look at raw pixels anymore. Layer 2 looks at the patterns of the edges.
Combinatorial logic.
Right. Layer 2 asks, do I see a vertical edge meeting a horizontal edge? If yes, boom, that's a corner. Do I see a curve meeting another curve? That's a circle.
So we're building the Legos. Layer 1 found the raw plastic. Layer 2 built the bricks.
And layer 3 builds the parts. It combines corners and circles to find wheels, eyes, snouts. And layer 4 combines the parts to find full objects. Wheels plus chassis equals car. Eyes plus snout plus fur equals dog.
It's a hierarchy, building from simple to complex.
It is. And the actual building block that makes this whole pipeline possible involves 3 specific steps. We call it the CNN block. Step 1 is convolution. That's the sliding window we just discussed. Step 2 is activation.
Activation. Okay, in the notes, this is listed as ReLU. R-E-L-U. Sound like a tiny robot from Star Wars.
Yeah, it stands for Rectified Linear Unit,
Yeah.
but honestly forget the technical name. Think of ReLU as the bouncer of the club.
The bouncer. I like that.
The convolution step is incredibly noisy. It finds edges, sure, but it also picks up a ton of garbage data backgrounds, static, weak signals, negative numbers. The bouncer's job is to clean all that up. It looks at every single number coming out of the filter. If a number is negative, meaning I'm not sure what this is or this isn't relevant, ReLU just turns it into a 0. It kills it.
Wow, ruthless.
It has to be. We only want the strong, clear, positive signals to pass through to the next layer. It makes the system nonlinear, which is just a fancy way of saying it. It allows the computer to understand complex, curvy shapes instead of just rigid straight lines.
So step 1, filter, finds the feature. Step 2, ReLU, cleans the signal. What's step 3?
Step 3 is pooling. And this is totally crucial for the Lego theory. Imagine you have a super high-resolution map of where every single microscopic edge is. It's too big. It's way too detailed. If the car in the picture moves 1 inch to the left, the map changes completely. That's bad.
Right. We need the computer to know it's a car, not exactly where every single atom of the car is located.
Exactly. So pooling takes a small section, say a 2x2 grid of the feature map, and just keeps the biggest number. It throws away the rest.
Polarizes.
It shrinks the image. It downsamples. It effectively says, look, I don't care exactly which exact pixel the edge was in. I just need to know there was an edge in this general area.
So as you go deeper and deeper into the network, the image gets smaller and smaller in terms of pixels.
But deeper and richer in terms of actual information. You lose the spatial resolution, but you gain semantic meaning.
Yeah.
By the time you get to the very end of the network, you don't even have an image anymore. You just have a list of probabilities. 98% car, 1% truck, 1% dog.
And this architecture, just stacking these blocks over and over, is what powered the huge AI boom of the 2010s.
All the famous models you might have heard of. VGG16, which is literally just stacking these blocks 16 times. ResNet, which figured out how to go 100 layers deep without the math breaking down. YOLO, you only look once, which optimized this process to run so incredibly fast it could detect objects in live real-time video. They all rely on this sliding window Lego theory.
It makes a lot of sense. It feels logical. It really mimics the biology of the eye. So why did we stop using it? Or at least, why did we move on from it as the gold standard?
Because of that very same sliding window. It's the greatest strength of the CNN, but it's also its fatal flaw.
How so?
The CNN focuses obsessively on neighbors. It looks at a pixel and its immediate surroundings. It really struggles to understand long-distance relationships.
Long-distance relationships, you mean between pixels?
Exactly. Imagine a picture of a cat where the tail is way down in the bottom left corner and the ear is way up in the top right corner.
Okay, they are far apart on the grid.
To the CNN, those are two completely separate, isolated events. The tail filter fires in the bottom left, the ear filter fires in the top right. To actually connect them, to realize they belong to the exact same cat, the information has to travel all the way up through the layers, getting compressed and squeezed until they finally meet at the very top.
It's like trying to pass a note across a crowded classroom by handing it person to person. It takes time, and the message might get garbled along the way.
That is a perfect analogy.
Right.
The CNN doesn't inherently see the global picture all at once. It has to crawl slowly across the image to figure it out. It has what we call a strong inductive bias for local features. It loves textures, but it sometimes totally misses the forest for the trees.
And I assume this is where Module 3 comes in, the paradigm shift.
Enter the Vision Transformer, or VIT. This is where we throw out the sliding window, we throw out the flashlight, and we start treating images like language.
This is the part I've been really waiting for, because transformers are what power ChatGPT, right? They're text models.
They are. They completely revolutionized natural language processing around 2017. And for a few years, the computer vision people were honestly jealous. They looked at the NLP people and said, hey, your models are learning context way better than ours.
Because language is entirely about context.
Exactly. Think about how you read a sentence. The quick brown fox jumps over the lazy dog. When you read the word jumps, your brain subconsciously connects it to fox the subject and dog the object.
Right. I'm holding the whole sentence in my head at once. I don't read jumps and immediately forget about the fox.
You are using attention. You are attending to the relevant words, ignoring the irrelevant ones, regardless of how far apart they are in the sentence. Transformers utilize a mechanism called self-attention to do this mathematically. And a few years ago, researchers asked a pretty crazy question. What if we treat an image not as a grid of pixels, but as a sentence of visual words?
Okay, unpack that. How do you turn a picture of a cat into a
You
sentence?
use a butcher knife, metaphorically speaking.
Sounds messy.
Step 1 is patching. Instead of sliding a window, we chop the image up into a rigid grid. Let's say we have our cat photo. We slice it into a 16 by 16 grid of squares. That's 256 squares total.
Like puzzle pieces.
Yes. Each of those squares, let's say one contains the cat's left ear, one contains the part of the whiskers, one contains a bit of the rug, is now treated as a separate token, a separate word.
Okay. But a square of pixels is still a 3D volume, right? It's still got the RGB layers. It's still a block of math.
It is. So step 2 is flattening. We take that little 3D patch, say 16 by 16 pixels with 3 color channels, and we squish it mathematically. We unroll it into a long single line of numbers, a linear vector.
So we literally turn the square into a string.
Exactly. Now, it really looks like a word in a computer's dictionary. We have a sequence of 256 visual words. Ear word, whisker word, tail word, rug word.
But wait, if we just have a bag of words, we lose the picture. If I take a jigsaw puzzle and dump all the pieces on the table, I don't see the image anymore. I just see a pile.
You just hit on the critical problem. When you shake a bag of words, you lose the structure. The ear patch doesn't know it's supposed to be next to the head patch. The transformer architecture has no inherent sense of space. It doesn't know up, down, left, or right.
So how do we fix that? Because space matters in a photo.
Step 3, positional encoding. This is basically like numbering the back of the puzzle pieces before you break it apart.
Cheat codes.
Essential cheat codes. We mathematically inject the location tag into each patch vector. We stamp the ear patch with a code that says, I belong in row 1, column 1. We stamp the nose patch with I belong in row 2, column 2.
Okay, so now the model has the content, the pixel data, ND, the context, the location.
Yes. And now the magic happens. The self-attention mechanism. This is the absolute brain of the transformer.
Walk me through it.
Imagine all these patches, all 256 of them, are standing in a massive conference room. And they all start talking to each other at the exact same time.
A cocktail party of image patches.
A very intense, highly caffeinated cocktail party. Every single patch asks every other patch one question. How relevant am I to you?
So the ear patch looks across the room at the nose patch.
And the math says, hey, we usually hang out together in cat pictures. We have a strong relationship. Let's pay attention to each other. The attention mechanism assigns a high weight, a high score to that relationship.
And then the ear patch looks at the generic beige rug patch down in the corner.
And says, I don't care about you, your background noise. Low attention score.
And this happens globally, across all 256 pieces.
Instantly and globally. This is the big difference. It doesn't matter if the ear's in the top corner and the tail's in the bottom corner. The attention mechanism links them directly. There is no crawling across the image anymore. The model sees the catness distributed across the whole image simultaneously.
That seems vastly more efficient for actually understanding the context of an image.
It is. The CNN looks at the local texture. It asks, is this fur? The vision transformer looks at the global context. It asks, is this a cat? But there is one final piece of the VIT puzzle that I find absolutely fascinating. It's what I call the power of zero.
The power of zero, what is that?
In the slide deck, look at the diagram of the VIT. Do you see the very first token in the sequence? It's labeled CLS.
Yeah, I see it. Position 0. But it doesn't correspond to any part of the image grid. It's just sort of there at the start.
It's a dummy patch. It contains zero initial information from the image itself. It's a blank slate, an empty vessel.
Why would we insert a completely blank patch into the sequence? We're trying to process data, not empty space.
Think of it as the conductor of the orchestra, or the scribe in a courtroom. It doesn't play an instrument. It doesn't testify. Its only job is to listen to everyone else.
Oh, so as the patches are all talking to each other at that cocktail party?
This dummy patch just listens. It aggregates the information. It absorbs the earness, the whiskerness, the tailness from all the other patches via the attention mechanism. It runs through the layers of the transformer, gathering the entire global context.
So by the end of the process...
By the end, this single token holds the summary representation of the entire image. If you want to know, is this a cat? You don't ask the ear patch. You don't ask the tail patch. You ask the CLS token. It holds the meaning.
That is profound, actually. It's like the model synthesizes all the chaotic visual data into a single pure concept held in that one vector.
It's the distillation of visual reality into pure math, which brings us perfectly to Module 4. Because that single concept held in a vector is the holy grail of modern AI. That is what we call an embedding.
Okay, the term embedding gets thrown around constantly in tech circles lately. Vector databases, embeddings latent space. It sounds like Star Trek technobabble. Let's really nail this down for the listener. Module 4, semantic awareness and multimodality.
This is the ultimate goal. We started today with a spreadsheet of 25 million numbers, the raw pixels. We want to end up with a small list of numbers, a vector that captures the meaning of the image.
We want to compress the file but keep the soul.
That is surprisingly poetic and technically very accurate. We call this the representation dilemma. How do you summarize a picture? In a CNN, we used pooling to sort of average things down locally. In a VIT, we use that CLS token. But the result is basically the same, a list of numbers, say 512 numbers.
Okay, so cat is now a list of 512 coordinates.
Yes. Imagine a graph. But instead of just your standard X, Y, and Z axes, imagine a graph with 512 axes. It's a hyperdimensional space.
Yeah, my brain absolutely cannot visualize 512 dimensions.
Yes, don't try to. We'll hurt yourself. Just imagine it as a specific location in a vast, infinite room. The cat vector lives at one specific coordinate in that room. The dog vector lives at a slightly different coordinate.
And I assume similar things live close together in this room.
Exactly. And this is how we validate if the model is actually learning anything useful. We compare pixel distance versus semantic similarity.
We have a slide on this, the house validation slide. Walk me through it.
Okay. Method 1, the naive approach. Imagine you have a digital photo of a house. Then you take a second photo of the exact same house, but you shift the camera maybe 1 inch to the right.
To me, they're the exact same photo.
To a human, yes. But if you do a direct, pixel by pixel subtraction method 1, the computer totally freaks out.
Why?
Because the underlying grid shifted. The white pixel of the window frame in image 1 has moved over. In image 2, that same coordinate might now be the dark pixel of the interior curtain. When the computer compares pixel 100, 100 in both images, the numbers are totally different.
The math says high error. It thinks these are totally different images just because the pixels don't align perfectly anymore.
Exactly. It is blind to content. It's checking the grid, not the house. It's completely failing the assignment.
Now look at method 2, semantic embedding.
Here, we don't compare the raw pixels at all. We feed both images through our VIT model. We get the embedding vector, the summary notes for the first image, and we get the embedding vector for the second image.
So we get 2 lists of 512 numbers.
Then we measure the angle between those 2 vectors in that 512-dimensional room. We call this cosine similarity.
And since both summaries describe a house with a window, the vectors should be pointing in roughly the exact same direction.
Exactly. The score comes back as a 0.99, a near-perfect match. Even if you rotate the cat, flip the house upside down, change the lighting from day to night, the concept remains totally stable in the vector space.
This is huge. We have finally severed the link to the raw pixels. We are operating entirely in the realm of concepts now.
And that stability is what unlocks the final frontier. The real reason why AI feels so unbelievably powerful right now, multimodality.
The convergence.
Think about it. We just figured out how to turn an image of a cat into a vector, a list of numbers that represents catness. But thanks to the NLP revolution, we also know how to turn text into vectors. We can feed the word cat into a text transformer, and it gives us a list of numbers that represents the concept of the word cat.
I think I see where this is going. If the models are good enough,
the vector for the photo of the cat and the vector for the word cat should be statistically identical. They should align in that exact same vector space.
that is the aha moment right there.
It is the Rosetta Stone of AI. For decades, text was text and images were images. They lived in completely different files processed by completely different software. Now, they're just coordinates in the exact same meeting space.
This is how Google image search works, isn't it? When I type beach at sunset into the search bar, I'm creating a text vector.
And the search engine just looks through its massive database of image vectors and finds the ones that are pointing in the same direction as your text vector. It doesn't look for the word beach in the file name. It looks for the concept of beach in the image content.
That is incredible. We've gone from a flat grid of dumb zeros and ones to a unified theory of meaning.
It's a journey from the matrix to the mind, in a way. And it's not just images and text. Audio waveforms, turn them into vectors. Video frames, turn them into vectors. MRI scans, vectors.
The universal requirement. Everything must become a number.
Once they are all in the exact same mathematical format, you can fuse them. You can have an AI that sees, hears, and reads all at once. That's multimodality. That is what we are seeing emerging right now with models like Gemini and GPT-4.
This has been a massive download. My brain feels like it's doing its own gradient descent right now, trying to optimize all this information. Let's do a quick recap of the journey for everyone listening.
Sure. Let's trace the arc. We started with the problem of sight, the cognitive gap. The computer sees a spreadsheet, we see reality.
Module 1, the raw material. Pixels are intensities from 0 to 255. Images are 3D stacks called RGB tensors.
Module 2, the Lego theory. We use CNNs in the sliding window to hunt for edges, then shapes, then objects.
Right.
We built perception from the bottom up, layer by layer, filtering the noise with our bouncer.
Module 3, the paradigm shift. We switched to vision transformers. We chopped the image into patches, treated them like words, and used self-attention to let the parts talk to each other to understand the global context.
And Module 4, the goal. We compressed that understanding into an embedding a semantic vector. And by aligning that visual vector with text vectors, we unlocked multimodality.
It's honestly amazing to think that every time I unlock my phone with my face or search for a photo in my gallery, this entire process, millions of calculations, high-dimensional geometry attention mechanisms, is happening in milliseconds.
It is. The machine isn't looking at the pixels of your face. It's comparing the vector of the live camera feed to the stored vector of your ID. It's pure math mimicking perception.
Which leaves us with a final thought to chew on from the notes.
It does. We've talked a lot about bridging the cognitive gap today. We always assume that humans see reality and computers just see numbers.
Right. We see the truth, they see the data.
But think about the embedding validation we discussed. The computer saw that the house was the exact same, even when the pixels were totally different. It ignored the lighting changes. It ignored the minor shifts. It saw the essence of the object.
While our human eyes might get tricked by an optical illusion, or we might miss a tiny detail because we're tired.
Exactly. If a machine can strip away the noise, ignore the shadows, and see the pure concept of an object mathematically, does it, in some ways, actually see more clearly than we do?
That is a little unsettling to think about, but also really cool.
It's the big question for the next decade of AI. Are we teaching them to see like us, or are we teaching them to see something we can't?
Professor, thank you for the lecture today. My notebook is completely full and my mind is sufficiently blown.
Class dismissed.
Thanks for listening to this deep dive. We'll see you all in the next one.